Hello, my name is Richard Thomas, professionally known as Richard C. Thomas. I'm a 3D artist and supervisor based in London. During the course of my career, I've had the privilege of working at companies such as Framestore, The Mill, I'm sure there's a few others. Currently, I am head of 3D for VFX Jellyfish Pictures. We make a wide variety of work. It's a really exciting time as we pivot more tasks into Houdini. If you do think you can contribute to the team, I'd love to hear from you. Outside of that, I enjoy writing articles about the industry and sharing tools with the community. Two of those such tools have made their way into SideFX Labs, and that's what I'm here to talk to you about today.
Here's a rough overview of what we'll be talking about. First up, why make PolySlicer? What was the intention behind it and what was the purpose? Followed up by a walkthrough for the interface. Then we'll illustrate some key concepts through practical examples, and then we'll build on these key concepts to try and create more complex effects and patterns. So why make the PolySlice? There are many ways to slice polygons in Houdini, like a clip node in a for loop or a Boolean operation. But what I found is as the complexity of the geometry increases, then often the computational cost and also the memory footprint increases exponentially. So at some point you hit a cliff where you just can't be moved beyond a certain level of detail. If one could come up with a way of slicing polygons that did increase linearly in its computational cost and memory footprint with the increase in complexity of the incoming geometry, and there's all kinds of production use cases that kind of open up. For example, city building patterns or automatic model geometry creation. If that threshold is raised in some way by that method, then lots of possibility opens up. So I create a core feature set that I wanted to achieve. These included a memory footprint and computational cost that would scale as linear as possible with the complexity of the incoming geometry. So the result would be super fast, ability to use in for loops and it kind of one after the other. And I wanted to present a simplest possible interface. It's super usable, felt very native, and then was intuitive. The next one was to control behavior with data from input geometry. So therefore, rather than just relying purely what's set on the interface, incoming geometry could have data upon it which would drive how those polygons were being sliced. I wanted to propagate attributes to the newly created geometry, including vertices and prims, so things like UVs would persist and make sense, and so texturing would work still, and perhaps other downstream nodes could be driven by it, like PolyExtrude, for example. And I want to control connectivity, so whether you could preserve the original connectivity or kind of break the slices per slice, or have none for some kind of like performance mode. Let's move on to the demo and see these core features at work. Okay, here we are. We have a basic pig's head test geometry. I'm just going to subdivide it once so you can see a bit clearly what the PolySlice is doing, get a sense of those slices. And here is the actual slicer tool here. I'm just going to walk through the interface really briefly to tell you what the different controls do. First of all, we have a group. Very simply, that's just a group of primitives or polygons that you want to slice. And then we have a mode. By default, it's set to polygon, but if you can switch it to polyline, then you actually get a line variant. So they're just polylines attached. Come back to polygon for now. And then we have a rest attribute, which basically, this allows you to toggle this on and specify a rest position that you want to slice. Then next is the visualization tab, which is basically the helpers. By default, we can show a guide to basically show the slicing. Okay, very simple. And then we have the option of coloring slices as well, again, just to see things a bit clearer. And then the next up is the dimensions, and this controls the actual slices, how many they are and the orientation. So let's just have a quick look. First up is the number of slices, pretty simple. You can go up pretty high with this. Obviously, there's an overhead, the higher, the more slices you have. Then we have the option to set bounding blocks, center, size, scale. So for example, you can change that. I'll just hit enter. I'm into the tool now, and you can see that I can freely change these change the inputs, and everything kind of updates at reasonable speed. Also rotation, things like that. And I've had quite a lot of interesting effects just by animating that, create some nice kind of glitch type stuff and motion graphic type things. Next up is topology. This section controls how the geometry is treated and basically how things are refused or separated, kept separate, etc., etc. So, for example, First comes divide convex. So basically the tool is designed to work with kind of planar faces. So this allows non-planar faces or complex faces to be sliced. And then next up is slice connectivity. So we have a few options here. We have skip connecting, which will not attempt to connect anything or reconnect it. So it's kind of more optimized. Then we have slices together. So it'll attempt to use the whole shell and re-establish it as it was coming in. And then we have slices separate. So each individual slice is separated into its own shell, essentially. So there won't be any connectivity between this slice and this slice. Border edge. So this is if you have specified a group, this will allow you to slice the actual edge outside the group and potentially rejoin it so you actually still get a consistent shell, watertight shell. And that's what this connect border edge setting does. And then it's some basic export settings. So this is like a slice ID, which is an integer attribute that lives on the polygon, which gives you a slice number per slice. And then we have export normalized slice, which is basically 0 to 1 float, which describes the actual value of the slice as you go through. So that's kind of useful sometimes to drive things if you're using ramps or something like that. And next up is export slice groups. So basically the new primitives that are exported will belong to that group. Then we have some cap stuff, which basically allows you to choose to export the extremities or not, like so, which creates some pretty interesting effects. And then we're left with the kind of advanced topology settings. These are quite important. So the defaults usually work pretty well. So the first one, point slice threshold, is kind of like as the tool's working, it allows it how close does an existing point need to be regarded as a slice point. And then fuse distance threshold. If you have a lot of slices, you may notice that that you need to increase this because this tool works in kind of like a slice space. So the more slices you have, the actual slices don't get smaller. The model going in or the model being processed is scaled up essentially. So as you increase slices, that space of the model, actually the actual size of the model going into the actual engine increases, and therefore the fuse distance needs to go up as floating precision errors come in. Hopefully that made some sense. And then next up is just a bit of fun. It's the ability to remap the slice position to get different effects. So you can essentially kind of just create different distances between slices. I mean, you can push this quite far, but you can see how, we have something uneven then. Okay, here we are with the pig set again. I'm just going to walk through some simple setups to give you some ideas, hopefully, of how to use the PolySlice in different ways. So here we are, just a simple slice, as I said before. And if we keep slices separate, and try to apply an attribute blur without pin border points, then you get something pretty interesting. You can really see what's going on with connections this way. So it's actually, as well as making some cool, interesting results, it's very good for diagnosing what's going on with your geometry connection. So, for example, you can say if I go slices together, you'll see how actually when I smooth, it no longer pulls apart because all the points are fused correctly. But then go back to slices separate. There you go. Every slice is separate. And if there is an issue, then in terms of connection, you'll see it as things pull apart. So again, adjusting the advanced section will probably help you out here. Fuse distance threshold is usually the likely thing to check out changing. If you see points stuck together, then usually this fuse distance is too large for the scale that you're working at. Yes, there's a basic slice. So one of my favorite thing again is just to basically drive the geometry with the slice ID. So you can kind of get these kind of weird offsets and kind of scaling graphic stuff. Kind of fun if you use the camera in certain ways. Now it also bears, it's also worth mentioning that you can also apply polygon slices in series. So you can build up interesting patterns. Really, to illustrate this point, I've just created another PolySlice at a different angle. I just re-enable the attribute blur. There you go. You can see everything is still working. It's just this additional layer of slicing on a new axis. So you can do this quite a lot as long as you're kind of careful with the scale you're operating up and you're kind of initializing things correctly. You can get some very interesting effects. So again, if we do the slices separate, you'll see I've got these interacting kind of patterns here emerging. There's so many things you can do and different effects, you know, as these different slice patterns interact. Okay, we've sliced the surface. Let's talk about how we can surface that slice. So here I have a PolySlice set to polyline mode, and I'm going to cycle over. And I found that using a polyfill set to triangles is pretty effective. Here I am just reassociating the polyline slice ID and CD. I found that when I created it, the polyfill did not propagate from the polyline. And then I'm left with just the actual surface itself. I clean off the original polyline exterior and I'm left with this. It's kind of weird, but yeah, high frequency kind of slice. And had some fun taking that slice ID attribute and just running an expression. And so that allows to create this kind of scan on effect. Can't see it, sorry about that. Scanning on effect, it's pretty cool. Picking up from our start point, you can also slice polygons and do a similar trick to actually surface those polygons. So here, looping over in much the same way, filling them up with the polyfill, running a bit of a surface offset. And if you look carefully, you can see, hopefully, all of the interior surfaces where you can't see. But trust me, there's interior surfaces. And then what I've done is just, again, based on connectivity, create a pack name. Basically prepped them up as pack primitives to be run for a sim. Here we are with the result of that simulation. I think it's quite interesting, quite promising. It shows you how when you reach a level of like geometric complexity and that you can pass it to a solver in a stable way, you can get some really interesting results. What happens if we start using this idea of rest? So here I've created the same geometry from the same point, sorry, and I'm just basically adding an attribute noise to break up the shapes and putting that to points. And so when I just enable the rest, it's set to rest. Let's give it a second. It's going to basically slice based on that rest. So it's very different to kind of with a non-rest. And we get much more organic shapes and swirls and things like that. And pretty much you can really think about this way to control the slicing itself. So at the moment I've got a very noisy rest, but you could actually put a much more kind of like non-organic, more kind of angular rest in there, and you'd get very different shapes. So yeah, I just kind of built upon this and just went to this bit further. I kind of offset some pieces like so, you know, drive with the usual, very similar to a normal method of just using the slice ID or normalized slice in this case, created here. And yeah, I thought it was pretty cool, pretty different. I ran it through a clean. I think there was a few degenerative primitives, but I'm not surprised given how crazy the input meshes or input rest, I should say, was. And then I just essentially simply extruded it out to create these organic shapes, like so, almost ripples. Done a bit of fixing down the way to fix the CD. Found that it was kind of misbehaving when I was extruding. The sides were being misbehaved. And yeah, just a bit of a attribute blur, and there we go. Thought it was pretty cool. Yeah, so I had a bit more fun. I basically started to proceed to run a simulation. I created some struts and thought, well, let's see what kind of shapes we get out of that. Okay, that's done. This is the result. It's very, very watery and kind of appropriate. Okay, let's talk about how we may go about creating less organic effects. Right here is a simple, well, right here is a city setup I've created. So here we have a plane to emulate the ground and some simple river-like patterns. I've just split them off, and then I use the UVs to create a rest position. This has been a really good approach for me because that means I can use the UV tool set to actually create interesting inputs to control how geometry is sliced. So I'm just putting the UV from this flatten into rest position, and then I just proceed to straighten some edges so the boundaries conform to the river a little bit. And I just do a simple blur, and I'm just pushing it back into the rest position and the point position. Quick remesh to kind of give us a more even starting point. And so then I just run a simple smooth just to kind of create a bit more evenness along the boundaries. That should help kind of how the blocks are formed along the riverfront. And then I create some connectivity attributes. Create a center attribute per island, and this will allow me to kind of vary the island, as you'll see later. This is the start point, and essentially what I'm doing is I'm transferring the detail attribute from the loop through into the main stream, and this is the point where I vary variance. And you see the ramp here, and what I'm doing is quick dive in. I'm essentially taking the detail attribute of what iteration it is and the prim center, and essentially just kind of scaling and varying, also adding some noise to create each iteration, to create a bit of variation between each iteration. So let's just check what that's doing. So here we are pushing it back into the rest space, and I'll just toggle that on and off for you so you can see that's what's kind of going on. Also see, like, what I'm doing here is I'm also offsetting in Z, and that helps recreate topology, because it means there's no overlapping or coincident points, which the PolySlicer doesn't like. And there's also a number of slices, so as the loops progress, it just runs up this ramp from 3 to 100.
And as you can see, I've got two PolySlicer nodes stacked one on top of the other at 90 degrees to create a sliced grid pattern.
Then I just do a bit of data wrangling, basically to make sure I can propagate what's been sliced. And I try to create this island attribute, and this is essentially based on what's been processed and connectivity, and then I just do a bit of a ID to prim to find the exact island number, do a measurement, and then I feed this into some logic. So what's occurring here is that out of all the things that have been processed, this allows those primitives to progress to the next iteration. So each thing that has been divided accumulates a kind of probability that becomes less and less likely. And then we randomly add some parts back in with some min area checks. The net result is some pretty interesting kind of cellular structures. I could easily, I'm doing it here actually. So if we actually take the square ID that which I create from the actual different slice attributes, and then run a divide on this, you'll see that I've turned on remove shared edges, and that creates these cells. So this could be useful for a lot of things. So things like footprints for buildings. That's how we're using it here, I guess, or just general patterns, whatever they may be. Maybe a network of some pipes or something like that. And then I'm just basically normalizing and prepping for the extrude. So I do an inset as long as there's some area there, and then I just extrude out for buildings. And the rest of it is essentially just coloring things based on groups. And the net result is this. Okay, let's pick up with a new base shape. I'm just going to run a very similar pattern to what we just created, with a bit less noise, so it feels a bit more techy and angular. Then I take that accumulated extrude value and just normalize it, kind of create some insets, and I offset it, and I get this base shape. Now what I'm going to do now is try and create a nice high frequency division pattern through iterating to get some like really fine greeble details. So let's just jump in here. So what I'm doing is it's a very similar start point. I just to the previous example, I just create a kind of rest position like this, 0 to 1, and propagate it down through into the loop itself. Again, I just very similar loop. It's a for each. It has set feedback, and it just transfers the detail attributes from the metadata. Again, I create some variants based on the actual rest position and kind of the island. I cycle over this stuff and then proceed to slice. Here we can see the rest position just going in like this. You'll notice that it's offset in Z to avoid any coincident points, which the PolySlicer doesn't like. As long as the points are kind of separated in the rest position, if they shouldn't be connected, that is, or if you don't want them connected, then everything all should be well. And then I just create some logic. I create an island based on connectivity of what's been sliced by blasting away everything that hasn't, and I just transfer it back. And then I just draw some, push this through into an extrude, just accumulate some extrude values based on the X and Y slice and also the iteration. So I get a random kind of value per island almost. Let's just look at this iteration as it accumulates. So I'm just going to go to wireframe so you can see a bit better. So I am modifying the max iteration so you can just see the accumulation of each stamp. So here's this one. There we go to 2. Each iteration builds up detail. Let's go a few more just so you can see you can see these kind of shapes that apply themselves and the patterns start to emerge. So unlike the previous example, you may notice that these kind of patches emerge. The previous example was more of a random kind of test where I create a random variable and then test against the threshold. This is actually a turbulence noise that is driven by an iteration and also testing to make sure we don't divide anything below a certain area. Okay, so you can see how the detail accumulates and accumulates and builds up, and then what we end up if we go for 20 loops, something like this, which is quite a lot of detail. I think this took about a minute to cook. And then just a very similar process as to when I create how I create the base shape and the city. They just offset and extrude. Just load this little stash here. And then you get this pretty complex, interesting pattern. I'll just pop up a render so you can see how detailed it is.
Thanks very much for listening. Hope you found it enjoyable and interesting. You can download this scene from my website, and you can also find a page that talks more in detail about technically how the tool works. I'd also like to take this opportunity to say thank you to the team at SideFX. It's been a really enjoyable process getting the tools into SideFX Labs. And I'd also encourage everyone out there to get involved with the community. It's been really rewarding for me over the last couple of years as I've become more involved. All right, have a good day. See ya.